Start this morning by telling you about a 12th century natural philosopher named Abelard of Bath. Abelard compiled a list of unanswered questions near the end of his long life. Among the 76 questions in his treatise on nature were those that interest an oceanographer like me. Why are the waters of the sea salty? Whence comes the ebb and flow of the tide? And why does the ocean not increase from the influx of the rivers? 9 centuries later, oceanographers are asking questions unfathomable to Abelard. How will navigation routes change as sea and land ice continue to melt? How are marine ecosystems faring in these warming waters? And will climate change cause the collapse of the ocean overturning circulation? If that last one puzzles you, let me explain. Ocean waters are constantly on the move. Many of the ocean waters are local, like the surface currents of the North Atlantic you see here. But the ocean is also home to large currents that travel from one ocean basin to the next, often thousands of kilometers away. The largest of these is referred to as the ocean overturning circulation. This current originates at high latitudes. In the winter, when cold winds blow across the ocean, warm surface waters are converted to cold waters. That's the orange arrow turning blue. These cold waters are now denser than the waters underneath, and so they sink and then spread at depth to distant parts of the globe, following that ribbon of blue. Eventually, these waters upwell, meaning they return to the surface where they warm, and so now the blue ribbon turns back to orange, and they return to where they started, completing the ocean overturning. Now, this ocean overturning redistributes heat on our planet. In partnership with the atmospheric circulation, this fluid movement maintains a 30 degrees Celsius difference between the equator and the poles. Without these fluid motions, that temperature difference would be 110 degrees Celsius, and not just over the ocean, inland as well. Polar latitudes would be completely frozen, and the tropics would be even more sweltering. But this overturning also impacts our climate, because when those waters sink, they carry with them the carbon dioxide they've gained by exchange with the atmosphere. And so as a result of this, as the decades have progressed, the amount of carbon taken up or fluxed into the ocean has been increasing in tandem with the increasing concentrations of carbon dioxide in the atmosphere. In fact, the ocean now stores 30% of the carbon dioxide released by humanity since the start of the Industrial Revolution. Now, this does mean that the levels of carbon dioxide in the atmosphere are less than they would be otherwise, which is good news. But that carbon uptake by the ocean increases ocean acidity, which is not good news for marine species that build skeletons and shells, and it is certainly not good news for marine ecosystems in general. Now, as our ocean continues to warm and as ice continues to melt, both of which cause surface waters to become less dense, we fully expect that at some point in winter, those surface waters will not get dense enough to sink. And at that point, we expect the overturning to slow. And if the overturning slows, well, there will be less carbon uptake by the ocean, but there will also be even more major disruptions to our climate and weather patterns. We can expect stronger hurricanes, even more intense precipitation. Just about now, you might be wondering, how quickly might the overturning change? Well, for decades, oceanographers assumed that the overturning changed slowly on the timescales of tens of thousands of years in concert with the ice ages. But a study in the 1990s of ice sheets, which hold bubbles of air from past climates, well, that study suggested that the overturning could change quickly, within decades, maybe even within years. And with that, the possibility of an abrupt collapse of the overturning circulation brought about by human-induced warming, well, at that point, it became a very real possibility. Thankfully, advances in climate modeling give us a much better idea today of that risk. The black and gray lines that you see on this graph are the model reconstructions of the past relatively steady overturning changes. The lines of various colors show you the future projections of the overturning based on different climate models and different climate scenarios. I'm going to start with the good news, and the good news is that the overturning is unlikely to collapse before 2100. Now, before anybody breathes a sigh of relief, I will remind you that our children, our grandchildren will likely see 2100. And really none of us are out of the woods because the overturning is likely to weaken over this century by between 11% and 34%. And that weakening is enough to cause the disruptions that I mentioned earlier. Now back to those various lines of color. All future projections show a decline, but they differ in how fast and by how much that decline will be. And this is exactly where observations come in, because the longer we measure, the better our predictions will be. If Abelard had started measuring 9 centuries ago, we would be way ahead of the game. Unfortunately, we only started measuring in this century when we had the resources and, frankly, the motivation to do so. One of those efforts is an international observing system in the subpolar North Atlantic. OSNAP stretches from the Labrador coast to one side of Greenland and then again from the other side of Greenland all the way over to the Scottish coast. Those red ribbons depict the surface currents, and those dark blue ribbons depict the deep currents of the ocean overturning circulation. Every black vertical line you see is a mooring that stretches from the sea surface to the seafloor, upon which instruments, shown as red dots, those instruments are on those moorings and they're measuring the ocean currents, the temperature, and the salinity. Every other summer since 2014, research vessels like this one have traced the OSNAP line, deploying instruments and taking measurements. Dozens of oceanographers from many different countries have been on these cruises. Here's a former student of mine off the coast of Greenland, bringing in a rosette of bottles that have captured water samples in the deep ocean. OSNAP also allows us to use new technology like this autonomous glider that once deployed will set off on a programmed course taking measurements at depth. Every now and again, this glider will pop to the surface and relay its information to a passing satellite. You could be sitting in a cafe, enjoying your latte, all the while downloading data from this glider, which for a seasick prone oceanographer like me is a godsend. However, it is true that conditions on these cruises are sometimes challenging, but I must admit that the views are almost always worth it. Now, you can tell from a glance that our OSNAP data to date do not tell us whether the overturning in this part of the ocean is currently increasing or decreasing. And the reason for that is the same reason that you cannot tell what the stock market will do in a year by looking at the Dow Jones Industrial Index for a week. There's noise in the market, and there is noise in the ocean. But just as we have confidence that stocks are a good bet in the long run, we have confidence that in the long run, the overturning will decline if our climate continues to warm. And with that confidence, we know that it's not enough for us to study the overturning in isolation. We need to understand how the overturning is impacting and being impacted by everything else going on in the ocean. I just told you the ocean is noisy. Well, the ocean is also connected. What's happening in one part of the ocean affects what's going on in another part. And so to understand and to improve our estimates of the overturning, the warming, the freshening, the acidification, we need to measure globally, and we are. This NOAA buoy is out there measuring the exchange of carbon between the ocean and the atmosphere. This one buoy is but a small part of a vast global measurement system that looks like this. Every line or dot you see on this map is where there is a ship, a mooring or a buoying out in the ocean taking measurements. This multinational effort is the backbone of 21st century oceanography. But we can do all those measurements of many things in many places, but to stem the warming, the freshening, the acidification, the sea level rise, and to reduce the very real risk of an overturning slowdown or shutdown, there's one solution. We must work collectively to reduce the carbon dioxide in our atmosphere. Abelard did not have everything figured out in the 12th century, and we certainly don't here in the 21st. Answers to Adelard's questions were centuries in the making.